Good day and welcome to today's grade 11 chemistry lesson on stoichiometric calculations. So what we will be doing today is just exploring how chemists predict outcomes of reactions using mole ratios, gas volumes, and concentrations. So this session is then designed to build a strong foundation using clear explanations and practical examples as we move along. Now, before we get into it, by the end of this lesson, you'll be able to define stoichiometry, perform basic calculations involving gas volumes and solution concentration, identify limiting reagents, and apply mole ratio to solve reaction problems. So don't worry, we will be doing it step by step, so it will not be overwhelming. Now, in terms of the lesson outline, what we have is basically the introduction to stoichiometry. What is stoichiometry? What do the textbooks say? And in simple terms, what is then stoichiometry? And why does stoichiometry matter? All right. And then we're going to look at the overview of the concepts used in stoichiometry in line with what is said in the caps, that is the molar volume of gases, concentration, limiting reagent, volume relationships, and volume relationships in gaseous reactions. And then from there, we will be working on examples as we go along, and then we'll obviously wrap up with a recap of what we have done. Now, stoichiometry, what is it? Now, it is a term which can be divided into two: stoichio, which means element, and metry, which means measure. All right, so these two terms have been combined to give us this thing which is called stoichiometry, which is just a measurement of elements. So this term was actually first coined by the German chemist Benjamin Richter, who then referred to it as the study of the relationship between quantities of reactants and products in a chemical reaction. So you see that term quantity, that is where that measure comes from, and it is then based on the law of conservation of mass. And remember, the law of conservation of mass tells us that matter cannot be created or destroyed during a chemical reaction. But remember, this chemical reaction of ours is in an isolated system. Others will even say in a closed system. So closed system, isolated system have a similar meaning. So that is what stoichiometry in essence is. So we're just measuring the elements, the chemical elements. So that is what we will be doing here. Now, let us start with the first concept, which is the molar volume of gases. Now, with the molar volume of gases, we are told that at standard temperature and pressure, which we call STP, 1 mole of gas equals to 22.4 decimeters cubed. So this is a standard unit that we need to know. So this value here is a known variable. So when you are given a question and they say they need you to calculate something at standard temperature and pressure, so you will know that that volume does not change. It is 22.4 decimeters cubed. All right, so that is the volume that we have. All right, and obviously how you are then going to calculate it in the form of an equation, you will say your volume equals to your number of moles, which is represented by N, multiplied by that value of 22.4 decimeter cubed. to get your volume of moles per decimeter cubed. All right, now let us look at the following example. Say for instance you're given 2 mole of oxygen gas at STP. So we need to then find the volume. Now, in order for us to find the volume of this, we need to multiply those 2 moles by 22.4. So it is going to be 22.4 times 2, which gives us 44.8 decimeter cubed. All right, so that is the volume of 2 moles of oxygen gas at STP. All right, now we're then going to look at the next component, which is our concentration. All right, now in science and specifically chemistry, there are formulas that guide how we calculate things. All right, now when we are calculating concentration, we are going to use the formula of concentration equals to number of moles divided by our volume. All right, now we can obviously play around with this what you call this formula to change the subject of the formula, because oftentimes you'd find that they actually gave you the concentration and they're looking for the volume. So you can then do that. You can use the number of moles and the concentration to find the volume, and sometimes you can also use the concentration and the volume to find the number of moles. It just depends on what they've given you. All right, so that is what this rearranged formula looks like. I'll be sharing a triangle later, which you can then use to visualize this thing. Now, with the example here, we are given 0.1 moles decimeter cubed. So this is a solution of sodium hydroxide. All right, so this solution is 0.1 mole decimeter cubed in 250 centimeters cubed. And as you can see here, we are working with decimeter cubed and centimeter cubed, and in our concentration, volume is always supposed to be measured in decimeters cubed. So you need to be very mindful of these units that we measure, these units. So what you then do is that the first thing that you need to do there is make sure that we are using the same standard. So you will have to first convert that 250 centimeters cubed into decimeters cubed. And how do we do that? The conversion tables are there, and to move from centimeters cubed to then decimeters cubed, you need to then divide by 1,000 decimeters cubed. I wrote multiplier is supposed to be divide by 1,000, and then you get your answer of 0.25 decimeters cubed. Now that we have our volume in the right unit of measurement, we are then going to calculate our number of moles. So here we need to find the number of moles, because we are looking for the mass. However, in order for us to get to the mass, we need to get to the number of moles. All right, so the number of moles here, we're going to rearrange our formula, and we're going to say number of moles equals to concentration times our volume. And our number of moles, which is the concentration of 0.1 that has been given there, and our volume, which is 0.25, which we have converted, gives us 0.025 moles. All right, now when you rearrange this formula, you are going to have a triangle like this. So this is how you're going to visualize everything. So whenever there's three elements that you are calculating, you need to know concentration equals to number of moles times volume. All right, now when you hide the concentration, that is the one that you're looking for, you can see that this is over this. And then say for instance you're looking for number of moles. When you hide the number of moles, you get your concentration times volume. So this line in between stands for multiplication, and obviously the one that looks like a division is in fact division. All right, so now we have our number of moles, but it doesn't stop there. All right, now we are looking for the mass. All right, now what we know about number of moles, we have another type of triangle that we can use when rearranging our formula. What we know is that we have our number of moles, and then we have our mass over our molar mass. All right, now in order for us to find our number of moles, we're going to cover this in, and we can see that the formula then gives us a mass over molar mass. So therefore the formula to then get our number of moles is this. However, in our problem, we have to find our mass, because we do know the number of moles. All right, and with the molar mass, we normally find it on the periodic table. So here we're going to take our number of moles multiplied by molar mass. All right, so which is basically 0.25 times 14, which gives us 1 gram. But one may ask, how did we get that 40, which is our molar mass? Now, in order for you to get to that 40, what needs to happen is that you're going to go to your periodic table and you're going to add up the molar masses of the elements which are there. So the chemical composition of sodium hydroxide is NaOH. So you're then going to look at the molar mass of sodium and the molar mass of oxygen, as well as the molar mass of hydrogen, and add them together. Now when you add them together, the molar mass of sodium is 23, the molar mass of oxygen is 16, and the molar mass of hydrogen is 1. 23 plus 16 plus 1 then gives us 40, and that is basically how we got to that 40, which we multiplied by to get our molar mass. And as a result, when we then multiply it with the number of moles, we then get our mass, which is 1 gram. All right, so this is just how we calculate our concentration. All right, so remember, concentration is how crowded the particles are. So that is it. Now let us then move on to the next element, which is limiting reagent. All right, now a limiting reagent is normally the reactant that stops first, or that rounds out first and stops the reaction. All right, so we used mole ratios from balanced equations in order for us to tackle this concept. It is very, very important in chemistry that whenever there's an equation, you balance it out. All right, now let us then go into an example. Say for instance that you are given 4 grams of hydrogen and 28 grams of nitrogen gas. All right, to make ammonia. Now let us then first write the equation of making ammonia. The equation of then making ammonia is N2 plus H2 to make NH3. All right, now this is already balanced. All right, and why do I say this is already balanced? As you can see, we looked at the number of hydrogens on the reactant side. Initially it was 2. Let me just go into the next one where I highlight the balancing, those coefficients. We initially had 2 nitrogens, all right, on the reactant side, and on the product side we only have 1, all right. So it means that we need 2 there, all right, but we don't put that 2 as yet. It is just what we're looking for. We know that we necessarily need to have 2, and then we move over to the hydrogens. When we look at the hydrogens, this side we have 2 and that side we had 3. Now we can see that, okay, fine, there's 2, there's 3. So how do we then balance the equation? If we multiply 2 by 3, then we will get to our 6, and that 2 then also applies for the nitrogen as well, and as a result our equation becomes balanced. Here what you normally do, you will test out from looking from the lowest common factor going upwards. So lowest starting from 2, you'll check. If I put 2 here and I multiply it by nitrogen, it's going to be 2 times 2, I get 2. 2 times hydrogen is 2 times 3, which is 6, which is fine here. And then also on the left hand side, it's 3 times 2, it's 6. 1 times 2 is 2. So the 1, we do not write it, but it is here, it is invisible. So that is now our balanced equation. All right, so that 3 and the 2, those are the coefficients to then balance out the equation. All right, now in this equation, before balancing it out, what do we know about it? What we know about it is that we have 1 mole of our nitrogen gas and 2 moles of hydrogen gas. One might say, but isn't this the same thing, because there's a subscript of 2 on the nitrogen and a subscript of 2 on the hydrogen? It's because of the number of protons. All right, so with nitrogen gas it is like this, and it is fine, it is 1 mole. However, when you then look at your hydrogen gas, the subscript 2 also represents the number of moles, because then there are 2 hydrogens there. All right, because remember, hydrogen only has 1 proton, and for it to be a gas you need 2 hydrogen elements. All right, now that is your 2 moles of hydrogen. All right, now when you then look at the balanced reaction, the balanced equation, now what we can see here is that in order for us to react 1 mole of ammonia of nitrogen with hydrogen to get that ammonia, we need to have 3 moles of hydrogen gas. However, what we then know here is that there is only 2, which means that our hydrogen is the limiting reagent. It's going to run out fast because we do not have enough. All right, we do not have enough hydrogen gas for us to react with the nitrogen. So that is then our limiting reagent. All right, now from there, what we are then going to do is say, okay, fine, we have determined that our hydrogen gas is the limiting reagent. All right, now from there, what we need to know is how many grams of ammonia are we then going to produce, given the amount of grams that of hydrogen that we have. All right, now we look at what we have here, we have our nitrogen, which is 28 grams. All right, so when we then calculate the molar mass of this one, we're then also going to go back to the periodic table, and our nitrogen gas is 14. All right, so remember that subscript 2, so there's 2, so you're going to say 14 times 2, which gives us 28, and the number of moles for this one is 1, because remember what they told us, 28 molar mass is 28 over 28, which gives us 1 mole. Same with the hydrogen. That is how we then got to our 2 moles of hydrogen. All right, now because this does not fully react, we are then going to do the mole ratio. All right, now when you do the mole ratio, you look at in a normal setting. So here we're going to then use our number of moles for ammonium, all right, to find out how much can we get when we use 2 moles of oxygen. All right, and then you will obviously calculate the molar mass of your ammonium, which is going to be our 14 plus 3. All right, so which is going to give us 17. All right, and then from there you calculate using what you've been given, and you then get your product. All right, due to time we're not going to go into it, but you know that you need to then go into your number of moles and your molar mass for ammonium. So we know that to get 1 mole, this is now our molar mass, and this is the ratio. You are then going to use the ratios, all right, of if we've got 2 moles of oxygen, and how many moles of ammonium are we going to then produce? Because in order for you to produce 1 mole, you then need 3, but that is fine. And then the product becomes 22.6 grams of ammonium. All right, now moving on to the next aspect, which is the volume relationships. In the gaseous reactions, this is where volume ratios apply. All right, so this is only for gaseous reactions. So we use the mole ratio, which is directly as the volume ratio. So the mole ratio and the volume ratio are the same. If we've got 1 mole, it means the volume is also 1. All right, if we've got 2 moles, it means also the volume is 2. So an example of ours here is that we've got methane gas and oxygen gas to then produce carbon dioxide and water. Now, when you look at this, the equation is initially not balanced. However, you have to first balance it. And when you balance it, there's then 2 oxygen gas on the left-hand side, which will then react with the methane to produce carbon dioxide and 2 water molecules. All right. Now, that means that in terms of our volume ratio, 1 volume of our methane needs to react with 2 volumes of oxygen gas to then produce 1 volume of carbon dioxide and 2 volumes of obviously the water vapor. All right, so this is how our relationships then work. All right, Now, what we have done in this lesson is just an overview of what stoichiometry is, and I gave one example each because this is a broad topic, but it was just to give you light in terms of how these relationships work. So remember, stoichiometry is there to help us predict outcomes using balanced equations. And what we then looked at was for molar volume, the concentration, the limiting reagents, as well as the mole ratios for gases. An important thing to note about stoichiometry is that we use it in various industries, such as your pharmaceuticals, your fertilizing industries, where you then need to be calculating such percentages. So there's many industries that use stoichiometry to predict and also to get desired results. So it's very important to then keep on practicing various calculations and the ones which have been provided to get to your answers. And understanding stoichiometry more, it is very important to get to the foundation, to understand the foundation, where it comes from, and why it is being done, especially in the day and age we're in. And yeah, make sure that you engage more with it. The term is normally very broad, or it seems scary. However, it is just the mathematics that we use in chemistry. And remember from the beginning story, which is the elements, which is our chemistry elements, and metry, which comes from our mathematics, which is to measure. All we're doing is measuring and figuring out the relationship between these quantities. Thank you for learning with me today. I hope you enjoyed the lesson.